Hello there, welcome to another session. So in the last couple of sessions we actually covered some rotation from a little bit more advanced perspective using vectors. So this time let's build on that. So here is things we covered. So if you have a point mass could be moving in a circle like that. We use this example to actually define a quantity called angular velocity. So this one probably you know. So this is the angular velocity vector. So here this vector will point in that direction. So from the definition you can tell that the V has to be perpendicular to both this and this. So V is perpendicular to both omega vector and r vector. That's how you can tell which way the omega will point. Okay. So basically you have you can think of a plane. So this is the r and this is the z. So there's this plane where we can extend, if you like, you can expand in 3 dimension. So this is a plane and V is perpendicular to that plane. Okay, so the omega vector is this direction and r vector is that direction, and you think of that forming a plane, and the V is perpendicular to that, and you use the right hand rule to figure out which way V will be. But of course you know V and you know this, and you're trying to figure out what direction omega will be. So if something is like rotating in a circle, omega will be perpendicular to that, so that's a kind of given, because V will always be tangential to the circle. Now we define angular momentum. So this is angular velocity, rotational velocity, and this called angular momentum. And for a particle of mass m, this is the fundamental definition. It's called r and v. From the v you make multiply by mass, get linear momentum, and you go to r cross p. Okay, this is a cross product. This is cross product. So if you don't know cross product, you have to go all the way to the vector things we talked before, long time ago. Okay, so what we did in last session was just take this, write this out in x, y, and z component. These are the unit vectors along that direction. And when you the way you do it is you replace this by this, and you just basically expand the whole thing out, and you find that you can write angular momentum as some x component times I hat, some y component times j hat, and some z component times k hat. Okay, so what are these components? Components depend on all components of this omega. So these are the omega x, omega y, omega z. Omega is written as omega x I hat. So over here is just, that will be 0, and omega y j hat, that will also be 0 in this case, plus omega z k hat. So here in this case, in this example, omega will be simply omega k hat. So this will be 0, this will be 0, it will just be this. So even if this angular velocity is pointing to the z direction, you see that angular momentum has an x component. It's not like the momentum. that would be the case of linear momentum. If the velocity is in linear momentum point towards the z-axis, then p will be in the z-axis. But here it's a little bit crazy. Omega is pointing along the z-axis, but you have an x component of angular momentum. Similarly, in this case, this will be 0, this will be 0, but this will not be 0. And we'll have this thing moving in a circle parallel to the xy plane. It still will have a y component of angular momentum. And the z-axis will be, this will be 0, this will be, and so of course this is expected. But things which multiply, they're not the same. These guys are different, okay? So there are these 9 things which have level I. They are called components of moment of inertia. And so moment of inertia is basically a collection of these 9 things. And sometimes each one of them is called moment of inertia. But this in particular is called moment of inertia about the z-axis. This one is called about the x-axis. This is called about the y-axis. But these guys don't have any names like that. And they just collectively called off-diagonal elements. So you can see what the formula came out. If you take a x diagonal element, then over here is no x. Okay? So this is basically radius away from the x-axis. How far away this mass is from the x-axis if it's rotated about the x-axis. That's not the case over there. So z will be just x squared plus y squared. And similarly for I, y, y, okay? The off-diagonal, basically whatever the subscript you put in there, they're the ones that get multiplied with mass. Of course, this is symmetric with yx replacement. So xy is same as yx. Like these guys are same. This and this are the same. And this is the same. So you don't have to compute 9 things. You have to compute 6 things in any system, okay? All right. So that's what was. Now I want to do some examples actually today. Now, and this we did for a single point mass. You can do any number of mass, just add them up vectorially. In particular, when you do what happens to these formulas when you have a continuous system, continuous mass system, kind of like a say you have a rod, and so what happens? It has a mass m and length l, and you can say, hey, it has a mass over length, density mass over length. So this is kind of things called linear density. So how did this formula kind of get replaced? You might have a disk. Say this is a thin disk, so this is infinitesimal thickness, and all the mass is here. So here's the mass, and then you say area. So you have an area is pi. So if this was circular disk, then this will be pi r square. Then we define density by mass over area, and this is not a linear density. This is also called density. It's called two-dimensional density. Okay, so two-dimensional density. And another way, continuous mass system. So say you have a some rock or something, okay? Well, it will have some mass and some volume. Then density is given sigma. This is sigma, and then this is rho, mass over volume. And this is a regular three-dimensional density. So this symbol is lambda. So those are lambda. These symbols are used normally in physics context. Okay. So let's see. Suppose we have this system, and we want to compute these things for that system. So how this will be? So let's say Ixx. So how this will be modified for this kind of system? Well, actually, you probably know. So this mass, and this is the coordinates of that mass. So this mass will be make it dm. So if I have a rod, so maybe it's, no, this is kind of hard to draw right now. Okay, let me draw it better, get a more space. And so these were axis, and then I'm going to draw the rod. Maybe the rod is along that axis. Let's call that y-axis. It's along the y-axis. So what you do is you look at infinitesimal thing. So in this little piece between y and y plus dy, so the little piece has length dy, and you say how much mass is there? Well, mass there will be dm. So you will write the moment inertia for Ixx for this quantity will be dm, and its coordinate will be x, y, z. In this case, this is 0 and this is 0. So you have a dm, and you have a y square plus z square. So this will be the formula for this tiny mass. And of course, if I sum this up, then I'm going to put Ixx, and this will be the formula like that. But the dm here, because the system is like that, how much mass there is, well, that depends on dy. So dm will be simply lambda times dy. So this this is called formally writing it. But then you write it out with this way, lambda dy. Now you can integrate, because this integration variable will over here will go from minus L over 2 to L over 2, minus L over 2 to L over 2 dy, and then that's the dm, and then you leave this y square plus z square. Of course, here z equal to 0, so this thing in this particular case is really easy to do, and let's do it out right away. So lambda is constant, so lambda here is m over L. So lambda is constant, pull this out, then I have integration dy with the limits minus L over 2 and L over 2, and times y square plus 0. So this whole thing is just 0 to L over 2 y squared dy, and you will get the formula that you're kind of very familiar with, 2 lambda, and then you're going to have y cube over 3, 0 L over 2, and so 2 over 3 m over L, and this will be L is cube over 8. Okay, so this cancels out one of them because L, and this cancels out, so make it this, so 1 over 12 ml square. So this is Ixx. So if it's rotated about that, you know, moment inertia will be that. this y-axis and this is z-axis. So you can see, you can just compute the same way. I zz should be 1/12 ml square. I think do it. You can argue from the symmetry of the situation, x-axis and z-axis here are the same symmetry, so you expect the same answer. How about Iyy? Iyy set up the same way. So this is going to be lambda dy, and because this is y, this is going to be x square plus z square. But each one of them is 0 for this element, this dm. If you look at the dm, dm is over here, and this x and z are 0, so this thing is 0. How about xy? X will be minus m becomes dm, formal like this, x and y. I really don't have to write anything because in this case this is always 0 because the rod is along the y-axis, x is 0, then this is 0. And similarly Ixz will be 0 and Iyz will be 0. So what we got is rod along the, so I have x-axis here, y-axis here, and z-axis here. If the rod was is like that, then we got xx is 1/12 ml square, 0 0 0 0 0 0 0. So rotation about this, we'll use this guy. Rotation about this, we'll use this guy. Rotation about this, we'll use that guy. And you can see they're all, because all the mass along this axis, there's no moment of inertia, no energy, no kinetic energy needed. Okay, so this is something that you're already familiar with, this calculation, maybe done before. Let's do something a little more interesting calculation. So involving, say, this area, let's do this calculation, okay? So of course, to do the calculation, we have we don't have just have a disk. This is the disk, and we have to do the axis. So we can have same axis as before, x, y, and z axis. And this is going to be over here. Let's do Izz first. Izz, okay? Just because that's the one you're kind of familiar with. So like rotation about this. This will simply be dm, and because this is diagonal, thing that will go in is x square plus y square. So basically we're looking at some small element of this dm. And if we want to integrate, because the limit is going to be along the radial, because we r 0 to r, integrating x and y variables is a little more complicated unnecessarily, and the theta will go all the way to 2 pi. That's the theta variable, and 0 theta less than 2 pi. Let's include that, okay? So less than 2 pi. So this is the integration that will cover the entire disk, cover all the masses. So it looks like dm could be written as sigma dx dy using x and y, but this element doesn't have to be that way. We can write down sigma r dr d theta. This is the polar coordinate. So we have a density. Here it's constant, but I can write sigma in terms of r and theta. But this, regardless of its density, is fixed here. Sigma is mass over pi r square. All right, so let's use this form, and then x is r cosine theta and y is r sine theta, and this just becomes r square. So this is simply sigma r dr d theta times r square, and it's a double integral, one theta, so there's two integrals here. Sigma comes out, and then we have a r cube, and it nicely separates out d theta. So there's nothing else, like you don't have to do one integral and then bring it in here and do that. It's very simple. 0 to 2 pi and 0 to r, and so all these integrals are very easy to do. So 2 pi sigma r to the power 4 over 4. I hope I'm not making any mistakes in algebra here. So putting back sigma m over pi r square r to the 4 over 4. So pi cancelled out, r square took away this, and to make it this. So you probably memorize this formula for rotation about this axis, and that's the z-axis here, and so this is the answer. So often people don't know how to do this calculation. How about ixx, iyy? So let's, of course, ixx by symmetry same as iyy. Okay, so let's do ixx. Okay, they're equal. So just do ixx, which is in the plane, axis in the plane of the disk, and formula will be just the same. It will be minus dm. Because I have x, I will use y square plus z square. Of course, z is 0 here because no matter what point you take, is z it's 0, so this not there, and y we wrote down like this. So the integration is now it's going to be minus dm will be sigma r dr d theta, that's the element, and this is the density, and y square is going to be r square sine square theta. So again, the integration really separates out very nicely. Sigma comes out, with r goes r cube dr 0 to r, and sine square theta d theta 0 to 2 pi. No dependent integrals, is very easy to do. Now this integral 0 to 2 pi sine square theta d theta. How do you do a square of sine instead of cosine? You divide by 2 and multiply by 2. So this converts this into a integral about 1 minus cosine 2 theta. So this is that. So half 0 to 2 pi d theta. So that's with this guy, minus half 0 to 2 pi cosine 2 theta d theta. So you can see that this cosine has gone into 2 cycles, and this will be 0, okay? And so this just gives me half times 2 pi, just a pi. So you got to remember this integral will come up again in doing other things in this problem. So we'll just remember it, and this will be r to the 4 over 4, and this just gives me pi, and minus m over pi r square, r to the power 4 pi over 4. So this is what, this is minus this plus, actually I put minus for no reason. Maybe I was thinking I'll do xy. Okay, so this is going to be 1/4 mr square. So this is the answer. Okay, so we did the diagonal parts. So looking at over here, we did for the x got 1/4 mr square, and for y got 1/4 mr square and half mr square, and we got this off diagonal elements left to do. Of course, this will be the same as that, and that will be same as that, and that will be same as that. So we don't need to do these guys down here, just have to do those guys. Okay, so let's do it out. Another, just let's see, do this guy out. That will be I xy, and that's going to be minus dm x times y. If you do I xz, it's going to be dm xz, but this is 0, z is 0, then this whole thing is 0, so I don't have to go further than that. But these guys are not 0, so let's see what will happen. Rho r dr d theta, and x and y, x r cosine theta, and that's r sine theta. So we have a minus rho r square r cube dr, and then sine theta cosine theta d theta. Now this is basically 0 to 2 pi sine theta cosine theta d theta. Again, I'm going to do double angle, half, then 2, this whole thing sine 2 theta. So it's a half 0 to 2 pi sine 2 theta d theta. And again, just like cosine, if you go in a, so this way, this is like a 2 theta will make one whole cycle in a pi, and another pi will make 2 cycles, and each cycle have positive area and negative area, they will cancel out. So this is actually 0, so this is 0. So going back, you have this guy 0, this guy 0, this guy, I will do this, okay? And so actually this will be all the 0, you just know why, figure it out. Okay, so that's a we got the disk. So that looks like a standard formula that we get. Maybe a nice one will be combining these in a cylinder of length L, radius R, and mass M. So how do you handle when you have a 3-dimensional situation like that, right? And you probably guess the formula, okay? And guess the approach, how I'm going to do it. Because whenever you have a cylindrical thing, you're going to have a polar coordinate in XY plane and the z-axis, right? That's called cylindrical coordinate. And that's the way to handle the integrals there. So we will again choose the coordinate axis just similarly, okay? So the system is symmetrically placed. So you have z goes from minus L over 2 L over 2. It's always good to write down what you expect. The R will be in the XY plane. In the XY plane, you will have distance from here will be R, and this angle will be theta, and R will go 0 to 2 pi, capital R, and theta will go from 0 to 2 pi, and dm will become volume density, and volume density is mass over the volume, and the dx, dy, dz, this thing will be replaced by the or the polar coordinate. This will be polar and this remain, okay? So r dr d theta, and the dz will remain the way it is. So this is the cylindrical coordinate volumes. Okay, so now we got this, and the volume is going to be pi r square L. So that's going to be what the rho will be in the end, okay? So this is the z-axis, and this is the x-axis, y-axis. So I'm going to say do I, z, z, I, x, y, I, x, z, and I, y, z yourself. Okay, do this yourself. And what I'm going to do is I, x, x, which should be equal to I, y. I'll do this by symmetry, right? There's no way to tell. You know, there's no unique direction. This is just perpendicular to that. There's only one. There's infinitely many direction in the perpendicular halfway bisector. So each one will have exactly same moment of inertia. So they should come out the same. You can check it by actually doing out the calculation yourself. All right. But I'm just going to do this part in the interest of time. So let's look. Let's do it very quickly again. So this is going to be, you have a dm, and that's going to be multiplying. I have x, so that's going to be y square plus z square. It's going to be no x here other than x. So the other guy is squared, okay? So that's the way to remember it. All right, so and of course y is going to be r sine theta, because we're in the polar coordinate. Of course x used to be r cosine theta, but we don't need it yet. So dm, so dm is going to be rho r dr d theta and dz, and this is r square sine square theta plus c square. And these are the things we have to integrate. Those are limits. So there are two integrations we have to do. Let's separate them out. Rho, this r with r becomes r cube dr, and sine square theta d theta, and then dz. And the limits are 0 to r, 0 to 2 pi, minus L over 2 to L over 2. That's coming from this part. And the next part is going to be rho, but this r is just r dr. D theta is just d theta. And then the z is z squared dz, and this is minus L over 2 to L over 2, 0 to 2 pi, 0 to r. Okay. All of these are elementary integrals. This we already done them. This is pi. Everything else elementary. Rho r to the power 4 over 4 times pi times L. This is going to be L. And this is going to be rho r square over 2 pi, and this is going to be 2 times 0 to that, right? Because this is symmetric integral. So even integral, right? Even, so 0 to L over 2. So 2 times 3 times L cube times 8. L L over 2q is basically LQ over 8. Okay, so now we need to simplify. So this 2 is going to cancel this to make it 4. This 2 will cancel this guy, make it so this 2 with this 3 and this 2 make it 12, and this is 4. So let's see, rho r square is common, pi is common, L is common. Let's take 12 out, then it's 3r square plus L square left. And this is pi square L. This whole thing is just mass. So this is mass over 12, 3r square plus L square. So you can see, you can check if r equal to 0 means just you're a thin rod, the one that we did that, then you just m over 12 L square, which is of course correct. So this is a looks like a correct formula for if I have a cylinder and if I drill a hole in the middle like that and put an axle through it and try to rotate it, so this is the moment inertia I will use. So this is like an x-axis, something like that. So this is Ixx will be the m over 12 3r square plus L square. So that's the one you're going to use for this rotating your cylinder in that fashion. Okay. All right. I think these are give you a picture of how we can compute pretty much anything. And in all of this situation, the axis we have chosen is they're all principal axes. So all the off diagonal elements, you can compute them, but they're all 0. Okay, and some of them I showed you that showed them explicitly that they're 0. Whenever you come to a system, as long as you can set up the integral in a way you can do the computation, that's actually part of the trick, how to set up the integral correctly. But once you set up the integral correctly with appropriate variables, whether you can use a cylindrical, polar, or spherical coordinate, those will be the common ones. If no symmetry is present, of course you go back to your Cartesian integrals, okay? And that should be okay. So next thing I'm going to do is actually talk about energy, like kinetic energy, and then we'll be ready to do problems like a precession and things like that. That should emerge naturally from our discussion of a little bit more complex examples in rotation, where you do need to think about vector nature of angular momentum. Okay. The reason I'm going on and on about it is the actual generalization of Newton's second law to rotation involved not only the change in magnitude of the angular momentum with time, but also change in the direction of the angular momentum with time. So the torque that you need to change angular momentum is actually can change, it may keep the angular momentum magnitude same, but it can change the angle, the direction of angular momentum, and that's very interesting. Those are interesting examples. Okay, that's all for now, and I will see you in another video. Bye.